Okay, please continue.
Okay, great. So let's get started with the final day here. So just to recap for people who were just joining us, the first thing we did was we constructed this two-category of trace open line algebras. Okay, the objects here were pairs A with a trace, A with a distinguished trace. The one morphisms were bimodules with composition given by confusion tensor product, and then the two morphisms were intertwiners. And so we talked about some other, we can also, from one morphism, we also have a notion of direct sum, but if this is something else, you can also take, there was conjugates, we talked about conjugation, and also down here we had an adjoint, so these are the two involutions. And moreover, we saw f star bar, this f bar star was this f check, which corresponded to the rotation of f. Okay, so this was something we saw, which we saw was equal to the other rotation. In the graphical calculus, so we also talked about the graphical calculus for all of this, compatible. Of course, we also talked about a bunch of coherence stuff as well, and that was what we did. And then after that, we talked about some subfactor stuff, right? We talked about this dualizability here was for when A and B were two unfactors. That's, in order to talk about dualizability, we went down to the sub-2 category where the objects were actually factors with their unique trace. So here, right, so for A contained in B, 2 and subfactor, we talked about right dimension, we talked about left dimension, we talked about the index, it's the left unknown dimension of the canonical L2 space, and then after that, eventually we got to, this was used for dualizability purposes. Let's see. Okay, and then we started talking about planar algebras. After planar algebras, right, this was a sequence of vector spaces with an action of planar tangles. As an example, we saw temporally Jones at a particular parameter of delta, and then there was the planar algebra modulus theorem, modulus rigidity theorem. Which saw that if we wanted the positive definiteness of all of the 2n box spaces to be positive definite, this means that delta is 2 cosine pi over k, such that k is greater than or equal to 3, union some number bigger than 2. Okay? So this was this Jones theorem. So I'm calling it now, instead of subfactor rigidity and index rigidity, I'm calling it planar algebra modulus rigidity, because we'll talk about the index rigidity toward the end of today. Okay, so this whole thing is the super quick review of what we did last week, Wednesday, Thursday, and Friday. That was just took 2 minutes. So now that if you're just joining us, that's what we did last time, and great. And now we're going to start, and hopefully today we'll have some self-contained stuff that if that'll just be presented from the beginning. But so we're going to continue our story about planar algebras here with actually how to build a planar algebra. The other thing we did, is that we went from this 2 category. If we started with A contained in B, a finite index subfactor. What we did was we looked at the 2 category generated by rho, which is the standard bimodule, and rho bar, which is the same, that's a BA bimodule, it's still L2B. And that was, we said, the standard invariant. Of A contained in B. And our goal is to show that the standard invariant forms a planar algebra. Okay? So in order to do that, the first thing I want to do is, it's easier to talk about unshaded, unoriented planar algebras like temporary leaf Jones. So I want to build, we're going to build an unshaded, unoriented planar algebra from a real bimodule. And real means that there is this unitary isomorphism which satisfies R bar composed with R is the identity, and because it's a unitary, and this basically just says that R bar is our inverse, which is R star. Another way to say this is R bar star, which is this R check, is exactly R, and so this also goes by the name of symmetrically self-dual. So, all right, this is the proof of actually an exercise I gave you, I think, on Friday, and great, it was a pretty easy exercise, but also these are spherical. This is a corollary here. Well, I mean, the fact that this is unitary, we see that dim A H is the same thing as dim A H bar, and this unitary tells us that because we can use RH, this is the same thing as the right dimension of H, and so this actually tells us spherical. All right, so I wrote on the board last time that it was spherical, and then I somehow got blackboard syndrome and forgot what I was doing, and I was like, I erased it. It is spherical. It's okay. Okay, so that's going to be important. In order to get an unshaded, unoriented planar algebra, it does have to be spherical. The loop parameter has to make sense from either side, and it has to be the same thing, so it really does have to be spherical. So how does one do this? The first thing I have to do is I have to give you what? A sequence of vector spaces and an action of planar tangles, right? So how does one define this planar algebra? So the first thing I want to do here is this real structure here, I can think of as the same thing as this conjugate linear unitary J.
And the name spherical comes from the way you draw it?
Yeah, it was the idea is that the planar isotopy happens on a sphere. Okay. So, or spherical / extremal was the other one. It corresponds to this minimal index conditional expectation that Yasu talked about as well. So this conjugate linear unitary J satisfies the following. 1, J squared is the identity. 2, if I want to know what J does to the bimodule structure, this is just the does this, and also 3, this inner product on H, J switches it around. Okay, so these are the properties of J. The point is I can trade R for J, and it helps to think about J when I'm defining this planar algebra structure, rather than having H bar around. I don't want H bar anywhere, I just want H's, and so I have to trade R for J. Okay, so I have to tell you what the nth box space is of this planar algebra. It's going to be HOM AA from L to A to the fusion of H n times, which we're going to call H super n. Okay, really it should be H box times, H super box times n, but I'm just going to write H super n to say that it's the nth fusion power. Okay, so I should think about this in the graphical calculus as elements in here look like boxes where there are n strings on top and no strings on the bottom. Okay, so I should think also that I had a yellow star last time for these. I'm not going to well, I could do it, but why not? Let's be consistent here. The star is happening right here, this yellow star in my planar algebra. So I should think about those things as just boxes with n strings out the top. That's my n box space, okay? And now I have to tell you how tangles act, but I'm going to tell you how particular tangles act and how that goes together. So the first thing is I want to tell you how a cap acts, and it's unshaded and oriented because all my regions are A, and this is just H. This corresponds to the following map. It's just, this is my evaluation pairing from H bar tends to H, from H bar fused with H to L2A, right? L2A is really up here. It's just this map, but remember now this real structure allows me to identify H bar with H. I'm really suppressing this R, right? Really there's a little R here, then it becomes H bar, and then it caps over. So this is exactly the map that sends, let's see, eta box times C. And here I'm just going to put a J here because I can always, if I have two bounded vectors, applying J to it is also bounded, so these guys live in H naught. This maps to the A valued inner product here, okay? That's what that map is, and then this map from L2A to H box times H, okay? This should be the map, this is A omega maps to the summation over beta of A beta box times J beta, where here, this is we talked about these, right? This is an HA basis, which we talked about as well when we were talking about duality. We talked about bases for these bimodules. Okay, so these satisfy the right things that they should. And then now the last thing I need in order to build a planar algebra is what happens if I have I strings here, an intertwiner here, and K strings here. I have to tell you what map that should be on the category, okay? Well, this is the map, so here I'm going to take C in HI bounded, or maybe I can do it the other way, H naught to the I, or it doesn't matter which one I pick by these density arguments. So this map is given by well, here F is an intertwiner from L2A to H to the J. It's going to map bounded vectors to bounded vectors, and the idea is I want to insert in between there, right? So it's going to map to the following. I take omega, which is my image of 1 in L2A. This is my cyclic trace vector. I apply F to it, and I stick it in here like this. Now, why is this map well defined? It has to be A middle linear. If I took a little a, right, the fact is that this region is the same region, so little elements of A should float back and forth here. If I have a little a here, moving it over here, I can do that because the fusion product here means that it satisfies that relation. Well, here, AF is AA bilinear, so I can map A in here, A comes out over here as well. So it's easy to see that this is AA middle linear, and thus well defined. Okay, so that's an important thing. And what we're actually seeing here is that there's an isomorphism. I think we did this, I might have said it, but if I have an AA bimodule, these HOMs from L2A to K is the same thing as these A prime intersect K, which is the central vectors. Okay, this was defined to be the set of zeta and K such that zeta is zeta A for all A and A. And importantly, this is a subset of both left and right bounded vectors. Okay, they're automatically left and right bounded by some. That was an exercise I gave, and the hint there is to use the fact that to look at the vector state for zeta, and then use the fact that a 2-1 factor has a unique trace. Fantastic. So great. So let's do an example, an explicit example of a tangle and the action that it does. Maybe I'll say here's a tangle, the rotation tangle, which I'll call, for lack of a better word, I'm just going to call it rotation. Okay, I don't want to call it R because that's there. I don't want to call it rho because that was some other map. Whatever, we'll call it rho because that map has been suppressed by now. We'll call it rho. Great. So this is rho. It's a rotation map. And let's figure out what it does. Well, I have to put in a vector, and well, here's the exercise. I'll just say so that rho is given by the following. It's given by summing over a basis, and I'm going to write L beta, R beta, star, where remember L beta was the left creation operator. Well, here, I'll tell you what it means. L beta here is going from, so we're always, what this map should be is a map from n things to n things. So rho is an AA endomorphism of h to the n, this annular tangle, right? This is actually a map, an AA endomorphism sorry, what am I doing? That's not what it is. Let's figure out what kind of a map, what is the domain of this map? It takes something in Pn, I haven't even said anything, so it takes something in Pn to something in Pn, right? Rho is a map from Pn to Pn. Yeah? What is it? A planar algebra, right? It's a sequence of vector spaces together with tangles give you linear maps. Yes, Henry?
So is the rho that element,
Rho
or
is
is
the
that
tangle.
the thing that takes the F and turns it into that?
It's the tangle, and it also is a map. I'm identifying the tangle with the map.
Okay.
So if I plug in something, it has to give out something as well. Okay. But rho is a map from Pn to Pn because that's what a planar algebra is. It's a sequence of vector spaces with an action of planar tangles. So anytime I give you a planar tangle, it has to give you a linear map on the vector spaces, right? So Pn was defined to be this, and we saw that this was isomorphic to Pn is just A prime intersect Hn as this. It's also H prime intersect Hn. So that there's some map from central vectors to central vectors that this rho gives. Okay, so I want to figure out what map that is. Okay, and in fact, L beta here is the map. It's going from Hn to Hn plus 1 by some bounded vector maps to C beta box times C. And R beta is similarly views on the right. Okay, so it's just a bounded vector here. All right. So it turns out that you can calculate that this L beta star. So really, here's the hint, I guess. L beta star of something, if I write, beta box times C, where this guy is in Hn minus 1 circle, and this guy is bounded in H. This is just, you take the inner product, the A-valued inner product, and multiply it by C. So this is like creation and annihilation vectors in like a usual Fox space model, for those of you who are familiar with that. And similarly, so these are nice formulas here. In particular, this can be shown, right, here we're creating by creating a beta and a J beta, and then we're inserting this thing in between, and then when we have this J beta and we annihilate on the right-hand side, you're going to get some inner product on the right-hand side, okay? So that's why you get this formula here, and this formula here for the rotation is originally due to Michael Burns in his thesis, which I think this is a very elegant definition of the rotation. It's really, that you can also do it with lots of conditional expectations, but this is really It's very, very elegant, as is the following proof that this thing is periodic of period n. I mean, it has to be, because the tangle is periodic with period n. So this map has to be periodic. So in fact, what one can show, okay, so here's the lemma. This is one of my favorite lemmas coming from Byrne's thesis. It says that if I take a central vector zeta, for every zeta here, for every c1 through cn in H, for bounded vectors in H, the inner product c1 box times up with cn with rho of zeta, and this is happening in Hn. I should give myself a little more space, but I don't want to erase. Okay, this is the same thing as now I have to figure out which way it's rotating. I think it's C2 box times Cn box times C1 with theta. Okay, so this is by density of linear sums of these types of things in Hn, by that density argument, we see that this exactly tells us that rho is n periodic. Okay, just by general Hilbert space density, right? If I had rho to the n, well, I can, every time I peel one off, I can move it over here, and so clearly rho to the n, if I peel off n times, the inner product of rho n of zeta with psi 1 through psi n is the same thing as the inner product of zeta with psi 1 through psi n. And that tells you here, it tells you this. Okay? And this is a really, really cool trick. So I'm going to prove it because I really like it. So it's a lot of
How
fun.
would you draw it in the figure that the row to the end is identical?
So if you look at that planar tangle here, that would be the same thing as
Let's say n equals to 2.
if I do this. Right, it's saying that really you can, 2 pi rotation is the identity. But that's essentially the point here. And what's the proof here? This is just a lovely proof, so I want to do it. So this well, I look at the formula for rho, so that's my formula. The basis is finite, so I'm just doing a finite sum here. Now I'm doing what's this? R beta star, L beta. Okay, oh, I already did the sum. Shouldn't be there twice. Now I take adjoints. Really fun what happens. R beta creates a beta on the right hand side, L beta star annihilates on this side. Now the fun happens. Okay. So what happens is this is just an inner product on an A bimodule. So, and this is an element of A, I can take its adjoint and it pops over here. Now I'm just going to call this guy, I don't want to rewrite it, but the idea is that this same vector here goes here, but this guy, the adjoint, comes here. And the adjoint just flips it. Okay? Now, this guy is an acentral vector. So he pops over to the other side, right? It commutes with zeta because it's acentral. And then, after it's on the other side, it can pop back over on the other side of the inner product. So now I'll write it again. C2 box times Cn, box times beta, but now it comes over as beta inner product with C1. And then here, this is just a zeta again. And you'll see that this, now that we sum over that, we get exactly C1 back. Okay, this is just exactly the property of a basis. Right? This is exactly L beta, the sum of L beta star applied to C1. So we get exactly C1 back, and that's the end of the proof. This is just a very, very elegant proof of the periodicity of the rotation. So I wanted to do an example of calculating the action of some tangle, so you see that. Great. So for the subfactor planar algebra, how do we get a planar algebra here? Well, I'm just going to tell you the same types of maps. These things satisfy some relations. I mean, the planar algebra stuff all really comes from the two-category formalism that we worked so hard to construct. So really, to understand it, we just have to understand it on some basic maps. So we should understand this map. So here I'm thinking about rho is L2b as an AB, and I write this by a row string, which is shaded over here. So the unshaded part is A, the shaded part is B. So I have to understand these maps. This is going from L2A to L2B fused with over B with L2B as an AA. So this is just L2B as an AA. Here it's from L2B to L2B fused over A with L2B. And then I have the adjoint maps. This is L2B as an AA to L2A, and then I have this one, L2B fused over A with L2B to L2B. Okay? So these are the first four maps to figure out what they're doing. This one's written first because it's the easiest. If A is contained in B and it's an inclusion of two unknown factors, well, the trace restricts to the other trace, right? It's really an inclusion of tracial von Neumann algebras where the trace is nice, and then this actually gives me an inclusion of L2 spaces. I'm going to call this I sub A, and that's this map, I sub A. All right? The other map is I sub B. It turns out that there's an inclusion because it's a finite index. Right? We worked pretty hard to show that if you have a finite index, there is an inclusion map here given by using the basis. This one's just the inclusion. A omega maps to A omega. Thinking of A inside B, this map was B omega maps to summation over beta of B beta box times J beta. Where again, beta is I guess it's a L2BA basis. One of these bases. What's next? We are doing, right, so here, these are just the adjoints, right? The adjoint of this map. So this is IA star. This is IB star. Okay? So, a little bit of, and then the insertion of the central vector is the same type of formula as insertion of central vectors, okay? So that's basically how you build a planar algebra and what happens. Oh, but here, the Pn, there is an interesting thing that happens. Pn plus is Hom AA from L2A to, right, so I'm telling you what tangles do, but I haven't told you the box spaces. Pn plus is Hom AA from L2A to, let's see, rho bar to the n. Okay, so here it's like saying this is the same planar out, like rho bar is L2b as an AA, right? But this isn't necessarily real. That's important to note here. The left A dimension of L2b does not have to be the right A dimension of L2b. That's an interesting thing to note here. And that is actually the source of quite a few issues here. If you're working with a minimal expectation, if A inside B has a minimal expectation, then it is real. But in general, this is not real, and that can be, this isn't just the same thing that we did before. Pn minus is Hom BB now from L2B to rho bar rho to the n as a BB. Okay, is that right? BB to the n or n plus 1? I either have it right or I have an off by 1 error. Only time will tell. Let me just circle this n to say maybe off by 1. Little question mark, I don't know. And we'll see later on, hopefully, we'll figure it out. All right, so that's what it is, basically, and the central vectors act in the same way, if you know. But great, in the last half hour, I want to actually talk a little bit more about the subfactor approach to these things, the actual, 2-1 factor approach to the planar algebra, the Vaughan Jones approach, okay? So this is an introduction to subfactor theory, and nowhere have I ever said the words basic construction. And so I feel like if Vaughan ever comes and looked at these lectures online, he would be like, Dave, what are you doing? So I feel like I should just do also a Neumann algebra approach. An actual subfactor approach, rather than the bimodule approach, the bimodule category theory approach. Right?
Check, is there a way of saying what rho bar rho is as a B module? Is it just L2B as a VB module?
No,
Or is it something else?
it's L2b box times over A, L2b. That's rho bar rho. Right, because when I write rho bar has an A action on here, and that has an A action, so when I write rho bar rho, it's fused there as a BB. It's the basic construction. We'll get to that if you're familiar with the subfactor terminology. And I actually, the point is I want to make this a little more concrete from a Neumann algebraic perspective. So, first thing we're going to do is we're going to just start with the subfactor, because we're starting with the subfactor and we're calling this 2 category the standard invariant here. There's another way to build it. So we start with this finite index subfactor. And as we said before, we get this inclusion. Okay? And then also we get a projection, or we have this is an inclusion, so it's an isometry, and then we get another partial isometry here. This is like a projection. So the idea here is that if I look at EA, which is IA star, so first I'll do, this is IA star. So the first thing I'll do is IA star, and then I'll do IA. Okay? So this is a map from L2B to L2B. Okay, and this is the orthogonal projection with range L2A. So often you can identify EA with IA, but we've been really careful so far the whole time, so let's continue to be really careful here. Okay?
Is the IA star, is that like the canonical endomorphism?
Nope.
Okay.
Nope. I mean, it's a partial isometry. It's not an endomorphism. This is that's like the type 3 lamb. This is the type 2 lamb. So this is So here's an exercise. EA is called the Jones projection. And here's some exercises that you can do. 1, EA commutes with a J. the conjugation. And 2, EA commutes with the action of A. Okay, so these are not so hard because IA commutes with the action of A, therefore IA star does, because A is a Von Neumann algebra, and therefore EA does. So that's how you do 2. 1 is also pretty easy. These are easy exercises. Here's the proposition. So Yasu talked about this, I think, in the first day of his course, which says, okay, for every B and B, there is a unique element EA of B, such that, and then here's the condition, EA, B, EA is capital EA of B, EA. And moreover, if I apply the projection to the vector B omega, I get exactly EA of B omega. Okay, so this goes directly to here. All right? So what this is saying is that if I take this Jones projection and I look at the image of B of B inside L2B, it actually maps into A, not into L2A. All right? And this EA is called the conditional expectation. Okay, and this is so how does one prove this proposition? So EA of B is actually equal to, and you can actually just write down the formula from the things we've already done here. It's IA star B IA, and this commutes with, this is a bounded operator in L2A, right? Because IA maps from here to here, IA star maps from here to here, so I'm just now acting by B in the middle. And now I just notice that this commutes with the right A action on L2A, so it's an A. Okay, JAJ is a commutant of A, so if I commute with JAJ, I have to actually be an A. Okay, and it satisfies a bunch of nice properties. In particular, it's completely positive. There's a whole bunch of things that you can do with it, and that's great. You can see the notes eventually for all the exercises that you prove about this thing. Great. So now we can talk about basic construction. So I look at L2B. It's got a left B action. It has a JBJ action on the right. This is B prime. That acts on the right. This B, I guess B actually acts on the right, not JBJ. JBJ is the left version of it. JBJ is what you call that algebra when you think about it acting from the left. So it's B action from the right. A acts on the left because A is included into B. This also tells us A acts on the right, right? I can restrict this. If I think about A prime, this B is B prime, right? This right action is B prime. So A prime actually contains this by like one of the first exercises we wrote, right? If A is contained in B, B prime is contained in A prime. Yeah? So there's an algebra missing. There's some algebra contains B and acts on the left. Well, everything, these bottom parts are done by conjugating J, by J to go over here. I conjugate by J to go here. If I conjugate by J backward, the basic construction of A inside B is the Von Neumann algebra J A prime J, which is also J A J prime, which lives in B of L2B. All right, and here's a fact. This basic construction algebra is the Von Neumann algebra generated by B and this Jones projection EA. Okay? So that's an interesting thing to prove. That's an index for subfactors. It's, great. And now the next interesting fact is that the index of the original subfactor being finite happens if and only if, sometimes we call it, we're going to use this notation, these brackets, BEA, because it's shorter. This happens if and only if this basic construction, the Neumann algebra, is a 2-1 factor. In this case, the index of the basic construction, or B inside the basic construction, is identical to the index of our original subfactor. So this is the notion of basic construction. So once we start with the subfactor, its finite index, and we can produce an overfactor of B with the same finite index. This tells us that we can iterate the procedure and get a whole tower of 2-1 factors. So I start with A inside B, which I think of as A0 inside A1. I adjoin E1. E1 will be EA to get basic construction algebra, which I'll call A2, and now at this point on top it becomes unwieldy to keep on, doing these brackets and putting in more algebra, I can look at now EB, which will be E2, get a Neumann algebra A3, and this happens on the representation of L2A2. I can now adjoin a projection E3 to get A4, and so forth, and this is what's called the Jones tower. Okay, so what happens here is the first interesting thing that happens. So let me just actually write down AN plus 1 is a Neumann algebra generated by AN and EN on L2 AN. Now, the first interesting theorem in the theory of subfactors is the following. This really is the first sign that something really interesting is happening. It says the projections EI satisfy the Temperley-Jones relations. So TLJ is the same TLJ that we talked about on Friday. First, EI squared is EI star is EI. 2, EI EJ is EJ EI anytime I minus j differs by at least 1. 3, EI plus or minus 1 EI is d to the minus 2 EI, where d squared, d is just the positive square root of the original index. Okay? So some people may have seen the diagrammatic temporally leaf algebras before. So the diagrammatic temporally leaf algebras are drawn with string diagrams. And you write them this way. So we talked about the temporally leaf Jones planar algebra. Well, one way to say this is that the temporally leaf Jones algebra, so maybe I'll say, so now I've got a notation problem. We talked about TLJ2n of this thing delta, which I'll use as D, and this was the vector space for the TLJ planar algebra, right? We saw it had a multiplication given by this. We saw it had an adjoint, which was given by the conjugate linear extension of reflection. okay? And then we saw that there was a trace. All right, so TLJ0 is nothing more than the complex numbers via the empty diagram mapping to 1. And here, this TLJ2n with this multiplication, that adjoint, this is a complex star algebra, sometimes called the temporally Jones algebra. And the problem is that I want to call it, I would love to have another notation for this, but I don't. So it's the nth temporally Jones algebra, and here I called it TLJ2n. So unfortunately, there's this 2n versus n discrepancy whenever you do this, and whenever somebody says TLJn, you should say, what do you mean by that? That's really the motto, okay? But what happens here is that, we get a representation pi n of star algebras, of complex star algebras, TLJ2n, going into, where are we going into? We're going to B of L2AN. Actually, so it's not just going in there, it's actually going into AN plus 1. So let's be careful about this. It's going into AN plus 1, sitting inside B of L2AN. By what? By ith thing, 1 over d, so this is of d, where d is the square root of the index, maps to EI, okay? These EIs satisfy the relations, and in fact, you can show that the abstract algebra generated by these diagrams is the same thing as the actual abstract algebra, okay? So the diagrammatic algebra is the abstract algebra.
Then maybe that should be TLJK.
TLJK?
Kaufman, yeah, he had a lot to do with this.
Yeah, so maybe I should call that KN. I could, yeah. TLJK, interesting, yeah. So these diagrams are called Kaufman diagrams. So I actually, I'm cheating here. I don't want to talk about the abstract algebra. I'm using the isomorphism between the abstract algebra and the diagrammatic algebra, which is certainly Kaufman. You're absolutely right. I could just write the abstract algebra and then just leave it with TLJ, but perhaps yes, TLJK would be, anyway, okay, great. Wonderful. And now, because here, this is bounded operators on Hilbert space, okay, what this says, and here trace maps to trace, that everything is matching up here. Here I actually should do 1 over d to the n in order to normalize everything, okay? But what happens here is that if I pull back the inner product from L2AN, right? In fact, what I'm also using here is an identification between central vectors and acentral vectors, some central vector identification between there and relative commutants, and allows me to pull back some inner products. And what happens here is that I get that we define here, yeah, x and y to be this trace actually. Here this is an plus 1 by trace of blank star blank, right? This is a, call this AB, call this B star A. Okay, so now it's okay. Let's not worry about it too much. Okay, so there's an inner product on L2AN plus 1 coming from trace AN plus 1 of this. Okay, so that's why we need this n plus 1 by trace n plus 1 of pi n of y star pi n of x. This here is positive definite this here will be positive semi-definite for every n. And this is positive definite for every n. And what it's telling us then is that this representation of the temporally leave algebra into this subfactor is giving me these positive semi-definite inner products on all of these temporally leave Jones algebras. And now, what this is saying is the only way that this can happen, right? We saw before that I stated this planar algebra modulus rigidity theorem. Last time I guess I stated also the corollary being Jones index rigidity theorem. These that one implies the other. So last time we had a theorem, planar algebra modulus rigidity. Says that if that these things on 2n on P2n are positive semi-definite, for every n greater than or equal to, this is on TLJ, are positive semi-definite for every n greater than 0. Actually, this happens if and only if. If and only if this modulus d is in 2 cosine pi over k, where k is greater than or equal to 3, union 2 to infinity. The corollary to this is Jones index rigidity. It says that the index of a subfactor must lie in the set 4 cos squared pi over k, k greater than or equal to 3, up to 4 to infinity. Infinity is always possible, so once you throw out infinity, then you can do this whole Jones tower machinery, and then you get this representation of the temporary leave Jones algebras, and then you use the planar algebra modulus rigidity to get the Jones index theory result, the Jones index rigidity result. Okay, so that's how I organize that in my brain these days. Okay. Fantastic. Now, from this perspective, from this whole von Neumann algebra perspective, what's the planar algebra? From the subfactor perspective, so what happens here? Well, what I have is this tower of algebras. Right? And so what I end up doing is I say Pn plus, because this is a shaded planar algebra. It's A0 prime intersect AN, so it's just the stuff in AN that commutes with A0. Right? So anytime I have an inclusion of algebras, I can talk about the relative centralizer of one inside the other. This is just the stuff in AN commuting with A0. Pn minus is defined to be A1 prime intersect AN plus 1. And now these spaces are exactly the spaces I already talked about. And that's what that's the last thing I want to do today. To argue why that's the case. And this is a nice connection between higher relative commutants and bimodules. So what's happening here? So the first fact is that L2 of AN is isomorphic to the n-fold fusion of n copies of L2b. And this is as a PQ bimodule, where P and Q live in a set A and B. Okay, so you can think about it as an AA bimodule, an AB bimodule, whatever you want. Okay, so that's the first fact that's going to get us off the ground.
Is this another way of describing what the basic construction is?
Yeah, you can do that too. Absolutely. But in order to get AN back out, you have to take the bounded vectors. So it turns out you can get it by taking A bounded vectors in there. You can get back the original algebra. And we can talk about that later. So here's the next proposition. There's an isomorphism, A0 prime intersect A2n, to endomorphisms of, and here I'm going to write L2an. So these two together give me my Pn pluses, let's put Pk pluses. This is n AB of L2an plus 1. If I look at A1 prime intersect A2n plus 1, that's n dB of L2n plus 1, and A1 prime intersect A2n is n BA of L2an. This gives me my BK minuses. And now that off by 1 error, I think actually was an off by 1 error, because here I have an n plus 1, not an n. So instead of having n copies of h, I think I needed n plus 1 copies of h, or whatever that was. Okay, whatever L2b or whatever was happening there. I do think it is an off by 1 error because this is p. Well, I'm just not sure. Anyway, off by 1 errors, I'm just going to ignore. Have you heard of the 2 most common mistakes in computer science? There's off by 1 errors. All right, so what goes on here? It's that the idea here to prove this proposition is that, so you have an acting from the left and right, and those are commutants. Here I can have any ak that lives inside an, acts from the left, and its commutant is actually an plus k living up here. There's actually a representation of on L2an all the way up to a2n, and its commutant is down here, a0. Okay, so using that you can prove this type of statement. There's really this multi-step basic construction thing is what's going on here to identify these relative commutants, because a0 prime you should think about that's commuting with the left a action. That's why end a appears here. This a0 prime is just end a. This a0 prime is this a commuting on the left. This guy here is y commutes with b. This a1 prime is y commutes with the left b. And then this algebra is talking about the right. This thing here is dealing with this thing here is this thing here, right? So this the commutant to the right a0 action is a2n, and that's why a0 prime intersect a2n is this. Okay. So finally, to identify the centralizer algebras with the spaces we talked about before, I just have to use this fact preceding the proposition. Okay, so I have so I'm thinking about things in here. I have 2 n strings on top, 2 n strings on the bottom, and some f in here. And each time I write, L2b as an AA bimodule, this is this, right? So A, B, A, because the strand was row and row bar, and when we saw row bar, it's just L2b, right? So that's why you see 2 n strings instead of n strings here. And then you do some Frobenius reciprocity. And then you can shift everything to the other side. And then I get 2n copies, okay? And so this is like taking all these strings and rotating them upward. Four n copies here. And if I want to do, say, a0 prime intersect a to n plus 1, so these are double strings, 2n plus 1 strings on top and 2n plus 1 strings on the bottom. What happens when I rotate them upward again? I get some f with 4n plus 2 strings here, and that's essentially giving you the, and then remember this is exactly central vectors as well by that previous result. That AA endomorphisms from the unit object into your bimodule is just central vectors. Okay? And that's what I have to say, that's it.
Okay. Thank you very much. Are there any more questions? Okay, thank you again for your thoughts. Thank you.